Deafness.
Good afternoon, everybody.
Could you switch off the
Alors, on va mettre un
microphone in
petit
Desiree?
arrête vers moi. Ouais.
Okay, good afternoon, everybody.
And then with Christof Rusli in
Yes,
Zurich.
Good afternoon, everybody.
Hi, Christof.
Hello. I give a short presentation about bone conduction in single-sided deafness. I will talk about some physiological aspects and clinical application. So bone conduction is an alternative to air conduction for the cochlea to receive sounds. Is the way we hear the noises of our body, such as breathing, flow of blood. And there are generally 4 different pathways accepted of how sound reaches the inner ear in bone conduction. One is the inertia of the middle ear and the perilymph. If the skull vibrates, there is a relative motion between the vibrating skull and the middle ear ossicles, and this motion stimulates the inner ear just like in air conduction. There is also a relative motion between the vibrating skull and the inner ear fluid. Second, there is sound radiated into the external auditory canal that evokes vibration of the tympanic membrane and the middle ear structures, the ossicles. Then there is compression and expansion of the otic capsule, and that generates a pressure gradient across the basilar membrane. And finally, there is some evidence of direct pressure transmission of sound via the cerebellospinal fluid. We don't really understand how the importance and frequency specificity of these different pathways. So in patients with single-sided deafness, there are different possibilities for rehabilitation. One possibility is a bone conduction hearing aid. But how does the sound travel from the site of stimulation to the hearing contralateral side? Is it a longitudinal wave across the skull? Is it a transversal wave? Or does it go directly through the skin? So we were interested in this question and performed experiments on cadaveric heads. We mounted an a bone conduction hearing aid on the right side, and it was directly driven in the frequency range of 100 to 10,000 hertz. We used a Baha cordel for this stimulation, and we used a LDV scanner to scan the superior posterior part of the skull. You can see here the skull that's lying on a rubber ring, and the grid indicates the area that was scanned. And we scanned 24 times 24 points. These points were about 5 millimeters apart. Then we also did a 3D measurements. We measured less points. We measured 20 points that were about 25 millimeters apart, but we used the same setup. And you can see here the experimental setup. So these are the results from the scanning laser. You see here the Baha cordel. This is the superior part of the head that was scanned, and for the low frequencies you can see a rigid body motion, and for the high frequencies at 6 kilohertz and above you can see a traveling wave from the site of stimulation to the contralateral side, and in between there was a complex mixture of rigid body motion and transversal wave. Just to be sure that we are talking about a transversal wave and not a longitudinal wave, we were interested in wave speed. We measured we calculated wave speed. We measured the distance between 2 peaks and took the curvature of the skull into consideration, and this gave us a wave speed of 450 to 500 milliseconds. We wanted to verify these measurements, and we used this time a single point laser that was pointed at the promontory, and we stimulated ipsi and contralateral and measured the vibration of the promontory. And this figure shows you the amplitude over the considered frequency range, and you can see from 300 to 700 hertz there is not much difference in amplitude that is consistent with a rigid body motion, but above 700 hertz the amplitude for ipsilateral stimulation is larger than for contralateral stimulation. And if we look at the phase, please just look at the solid line and don't forget the dashed line. Red is ipsilateral stimulation and blue is contralateral stimulation. And you can see here the roll-off of the phase, and this roll-off confirms a time difference of 0.4 to 0.5 milliseconds. So we can be sure that there is a traveling wave that puts the promontory on the contralateral side into vibration. These are the results from the 3D lasers. It's a busy slide. You can see on the top line the results for stimulation of 500 hertz and the lower line for 8 kilohertz. And this is amplitude and phase for the 3 measured axis. So x-axis is here, y-axis is up and down, and z-axis is in and out. So the z-axis is the same axis as was measured with the scanning laser. And you can see here indications of a rigid body motion, and here indications of a traveling wave. Another way of looking at this data is to plot the ratio of the different motion components to the total motion. You can see in the low frequencies the x-axis is dominant, consistent with a rigid body motion, and in the higher frequencies the z-axis, the in and out motion, is dominant, consistent with a transversal wave propagation. So we were interested in how a bone conduction hearing aid works in patients, and we used a bone bridge for this clinical study. As you know, a bone bridge can be placed in the mastoid if there is sufficient space. If there is not enough space, it can be placed retrosigmoidal. That's not a problem, and sometimes planning is required. There are different software tools where you can, on a computer, move the device virtually into the right position. That's an example of a very small temporal bone. You can see that's not the perfect space. So these are the results of our 9 first patients with a single-sided deafness, and we tested speech understanding in noise. We used the Oldenburger sentence test in 3 different situations. In situation A, signal and noise came from front. In situation 2, noise came from front and signal from the good hearing ear. And in the 3rd situation, noise came from front and the signal from the contralateral ear, from the deaf ear that had the bone bridge. And this figure shows the results for situation 1, 2, and 3, and it compares the unaided versus the aided situation, and the signal noise is plotted here. A lower value is better. So here we can see in situation 1 and 2, there is no significant difference. That means the device does not disturb understanding. And in this situation where we want to have the sound amplified and brought to the good hearing ear, we can see a significant improvement of speech understanding in noise after 12 months. In 6 of our patients, we had several measurements over time, and this figure shows improvement or change of signal-to-noise ratio. And you can see at the first fit there was no significant difference. Only after 6 months we could see a significant difference of unaided and aided thresholds, and this difference remained after 12 months. So this means there is a learning curve, and I think it's very important to counsel our patients accordingly and tell them it needs training, it needs time, and it's not just you switch the device on and it works. It needs some training. So I'm already towards the end of my presentation. I hope I could show you that it's well possible to use bone conduction hearing aids for patients with single-sided deafness, and that traveling wave is dominant in the high frequencies and the rigid body motion is dominant in the low frequencies of how sound travels from the site of stimulation to the contralateral ear. A bone conduction hearing aid requires sufficient space for implantation, and the hearing and it requires also a rather good hearing on the contralateral side. So you have to be sure that the contralateral side has sufficient good hearing. The surgery depends on the device and anatomy, so there are different possibilities. A bone bridge can be used, as in our clinical study, but there is also the Ponto or the Baha. And the results are comparable for different bone conduction hearing aids. So I would thank the research team in Zurich, and I'm happy to take questions if there are any questions.
Thank you very much, Christof. I guess the obvious question is, do the patients use the hearing aids and feel that there's benefit?
Yes, they do. In this study I showed you, we used a questionnaire as well, and most of the patients have a good benefit. So they use it often, they use it every day, and they're happy. They're happy with the hearing sensation they have.